Yeah, in my other house, I had also a big, bunch of bookshelves filled with books. And then I moved to a house that didn't have bookshelves. And now they're all in storage.
Right. Um, most of these are my wife's and my daughter's. So I have like kind of the middle section, but there's something comforting about having books. Yeah, whether they're on the shelf or they're in the box or
Absolutely.
like knowing I have them. So
You know,
and
I I
Mhm.
I I feel for you because in my house I also have a narrow set of shelves where my clothes go.
Right. Yeah, I had a friend. What did he call it? He called the walk-in closet the hers and she closet, and I said that's about right.
Yeah.
So yeah. Anyway, I'm excited to talk about GAN, and it's one of my favorite topics these days. I've been busy with GAN for a long time, so I'm hoping to talk about a few things today. One of them is that GAN isn't really just for switching devices. We use a lot of GAN in linear applications. You and I will have a sidebar discussion because it looks like a lot of devices that we're using are not recommended for new design, but there's also not a great replacement for them. Um, and so
And
we'll talk about one of these.
there's no plan to discontinue them at
Yeah,
all. So no
yeah,
worry
and
there.
yeah, we can. I mean, we can buy a big storage too if we're worried about it. Right now, we're not worried about it. But I want to talk about gallium nitride in linear applications, and I also want to talk about um, different kinds of GaN, and I want to talk about the difficulties. The difficulties we have aren't really electronic at all at this point. The difficulties we have are cooling them, and only because we have to get to these ludicrous power densities. And so I'm going to talk a little bit about why these power densities are getting to where they're getting, and why it is that it needs to be GaN, and why it is that these GaN devices need to be so small. Um, there's a lot of challenges here, and not only did we have to learn to work with the GaN devices at these power levels, but we had other challenges too, even in addition to the cooling. We had to custom design resistors because we couldn't find resistors that could do what we needed them to do. And so we designed new three-terminal resistors that have near-field cancellation in them. And we designed two-terminal resistors that are designed specifically to be water-cooled. And those made up with a manifold that's sort of in braille, and you can probably see those channels there.
Wow. That is
Um,
amazing.
right, those channels are designed to lay right across our custom two-terminal resistors. And the reason that we had to design our own resistors is we have customers doing things like this. That's one of our high-powered loads.
Hmm.
That's 65-volt 3-amp load, and it goes inside one of our probe tips. Um, and it's a real challenge because we're putting a couple of hundred watts into a 1-watt resistor and just cooling the crap out of it using refrigerated liquid cooling. But that seems to work. And so um, the project itself, designing this load cell took us almost 5 years. And now that we have the load cell, we're just putting in all different kinds of spaces. So the biggest one is the one that you have. That's the 100 millimeter socket that has, 2000 watts and 512 GaN devices and almost 1200 drivers. This is probably the most thermally challenging, and that is for testing power supply rejection of um, high power transceivers, the 224 gigabit transceivers, and now NVIDIA has a 3 terabit transceiver. And so the difficulty is that they have this transceiver and they want to modulate the power line, the 3.3-volt power line that's consuming about 12 amps, and they want to modulate it to 200 megahertz. NVIDIA wants to modulate it to a gigahertz. And so one of the things that came up is that the only way you could do that is if you remove the connection, because the connection itself is highly inductive, and you get a low impedance modulator and a low impedance input, you'd never get anything through the wire. And that's how they became probes. Making it into a probe didn't get rid of the power dissipation, it just moved it closer to the transceiver. And so now we had to get the cooling to the transceiver, and that's how that came to be. The most challenging device we've ever done is this one. It's a line modulator that we made for the 48-volt data center bus. and 2000 amps to a card that's 50 amps. So we need to be able to modulate 50 amps at high frequency. There's one device in here. It's one of your devices, 12 square millimeters, and we have 140 watts in it. Um,
Wow.
so roughly 12 watts per square millimeter. From the cooling perspective, that's the most difficult challenge we've accomplished so far with gallium nitride. And so this is
So
kind of
at
to that.
120 watts, you're looking at getting down to about you know, 1 degree C per watt in thermal conductivity of that system, which is amazing.
Yeah. Um, yeah, I would say it's quite a challenge. Um, the biggest challenge being the thermal paste. We can have 80 degrees across the thermal paste if we can hold it to a
Yeah.
5 mil thickness. And that includes all our tolerances and stuff. So we do have a lot of beta materials for companies that are testing higher conductivity paste. Of course, the device is really tiny. How do you manage to get a uniform 5 mil thickness? It's kind of challenging. So the interesting thing is that mastering gallium nitride wasn't hard, especially for your gallium nitride, because yours appears to be unconditionally stable and your competitors is not. And that makes it even more challenging. So we like using your devices because of that. They're also really small. They have low thermal impedance and they're inexpensive. So a lot of pros. In fact, there's a lot of discussion going on in LinkedIn about, not understanding why it is everybody's excited about gallium nitride, because if you're not switching at high frequency, what's the point? And I said the point is lower resistance, smaller size, lower capacitance, higher bandwidth. Um, there's 100 benefits other than switching. And so that's why I wanted to make sure we talk a little bit about the fact that we are doing some digital stuff. Our load, this load is a digital load. We're just switching a matrix of resistors. In other applications, they're linear, and even our loads, we have linear loads. They have different challenges, um, but we're exploiting the heck out of it. And the point was that we can actually switch right now at 1,000 amps per nanosecond. And that's not actually limited to the gallium nitride at all. That's limited by the board. And so now we have customers asking, can you do higher power? Can you do higher power density? Can you get higher speed? And so who's building these crazy high speed things? I don't know. Um, I know a few of them, but I don't know what devices they're actually powering. But they're actually trying to synthesize die that are switching close to a gigahertz.
Yeah, we also have LiDAR customers that are switching, you know, 300 amp per nanosecond
Yeah,
uh, and more. So that would
yeah,
be another one, but that's like a load transient, right?
for sure, for sure. And we're right now we're at 1,000 amps per nanosecond. That's limited mostly by the board. And LiDAR, you're limited by the board and also by the diode, right? The
Yes.
diode is a significant limit. Also, you're doing higher currency using larger devices. But one of the things we pointed out, a lot of the work that I did over the 5 years was paid for by a customer, and they really needed us to finish this development. But one of the conclusions was that the speed of the device is L over R, and L is the inductance through the power path, obviously, and
Yeah.
R is the resistance of your load, and that says the more current you switch, the slower it's going to get. So could we switch faster? Of course, we have to switch less current per device. That's why we're using such small devices, right? The device we're
Mhm.
using has a 1 picofarad CGD. It's pretty easy to switch that one really quick. If we made it a big device, we wouldn't be able to. Of course, we could parallel lots of devices in a switch application, but we can't in a linear application. So there are lots of challenges, but I don't want people to be afraid of gallium nitride either. Gallium nitride is great stuff. It's got an awful lot of benefits other than switching. And so I think that that is really important for engineers to understand. This isn't really just about how fast can you switch.
Yeah. Anyway, you know, look, these devices that you're using the device at the bleeding edge, and it's amazing. You know, can you maybe talk about some of the difficulties you had in the early stages other than thermal? Did you have any problems with paralleling?
Oh yeah. I mean, we tried lots of different things at the beginning. We tried just directly paralleling gallium nitride devices, and that got really interesting. Part of because of the temperature biased instabilities, partly because it's really hard to match the power paths. And we started out really simply. Um, and this is even before a customer got involved. We just wanted to see how fast we could make one of your devices switch. And for me, it was really at the time just a challenge. And we switched one of your devices in about 140 picoseconds. And I wanted to publish that. So before we did, we asked Langer to measure the same device. And then we ended up selling that as a probe tester. We charge up, the probe tip capacitance to a high voltage, and then we just discharge it through a GaN FET, and we can watch the response, and we can look at FFTs and stuff in the scope. And so I wrote an article titled, "How Fast is GaN Fast?" And that 140 picosecond device was really just for us to see where the limit was. And from that, we got to this little probe tip thing. We had two customers that asked us to do that. And again, it was the same problem. They needed really high bandwidth, which means you can't really have interconnects. But they wanted to be able to switch relatively high power. NASA wanted to be able to switch 120-volt bus, and Qorvo was switching a 65-volt bus to their pulse radar. And so we focused really on the Qorvo thing. We did NASA's too, but we focused on Qorvo because Qorvo had an interesting requirement. They wanted to make sure that the load step could get to at least a 700 megahertz bandwidth. So we had to build this device that was a load cell inside a probe tip that would switch 65 volts at 3 amps at 700 megahertz. And interestingly, they did it. We delivered the probe. They were able to use it in their test, and they actually published an article in, I think it's Power Systems Design by Masashi Nagawa, and he wrote an article about step loading his high voltage power supply. And he did show our little probe, and he even used near field extractions to actually measure the bandwidth at 700 megahertz. So we kind of hit that on the mark at 500 picoseconds on their 65-volt bus. And so that got into the probe tip. But as we started developing things, customers wanted more difficult solutions, right? I mean, it never stops. Engineers really love it. If you could do 500 megahertz, you ought to be able to do 5 gigahertz, right? So what does it take to do that? And so we started, building bigger arrays. And in the larger arrays, we built actually two different types of loads. One was an active load where we used, op-amp feedback. That also, we couldn't parallel devices for the same reason, temperature bias instabilities and even control loop stability. And so we had to have 1 amp op amp per gallium nitride device. And the goal was to hit 300 megahertz bandwidth in this control loop feedback. We actually did hit 2 nanoseconds, which is about 175 megahertz roughly in a closed loop configuration. And it works fine. The power density is much lower because you have to add the op amps, and there are little other complexities. For the example, we can't use a control voltage because these cells are divided across a large array, and ground bounce would say that they're all going to end up seeing different control voltages as they bounce. So we had to develop current programming so that we could feed constant currents into the programming control limits. And we did it. In fact, we're going to have it in a probe next month. It'll be in a housing just like this one, and it'll be able to do up to about 50 amps and 50 watts in a probe tip using closed loop feedback. For real speed, we really needed to do something different, and so we decided that the best thing to do was just to switch resistors, and we could switch resistors in a huge array. We could control the resistors. The only problem was we couldn't find resistors that were designed for water cooling and that could take the kind of power that we wanted to deliver. And so we worked with thin film technology to design two resistors. We designed one resistor that's specifically for water cooling. It's a wide geometry resistor for low inductance. And so far, we've put about 40 watts into a 508 package. We're trying to figure out what it
Wow.
takes to kill one. We haven't actually killed one yet. The other resistor is more interesting. It's a 3-terminal resistor. We asked them to add a foil layer over the film and bring that out as the third terminal. So we're actually connecting the near field from the resistor into this foil, which is connected as a common mode transformer. So it removes the inductive part of the current sense resistor. It's not perfect, it doesn't remove it, but it does raise the bandwidth of the resistor about 10 dB 3x, significant. And so we worked with thin film technology to make these two resistors for our loads, and it took a while to do that, but we pulled it off. Once we got through that, the next challenge was even bigger, really, because now we had to figure out how we were going to cool this 100 millimeter by 100 millimeter array that's got 2 kilowatts in it. We're not really experts in cooling systems, but we had to design the manifolds and we had to design the cooling system ourselves. We even make the pumps, we buy Alpha Cool's pumps, but we make the pump assembly ourselves. We needed to learn how to do that. And once we learned to do that, we had yet another problem. That is, to test the 2000 amp load, you need to have a 2000 amp power supply. And of course, since the speed of our load is determined largely by the design of that circuit board, we needed the details of the circuit board. So we started shopping around to see if any of the big semiconductor companies had eval boards that would be in the 2000 amp class. And interestingly, some of them did. They wouldn't lend them to us, but they had these terminal blocks all the way around the outside perimeter of their board. And they said, what's that for? And they said, that's for the step loads. And I said, well, that ain't gonna work. The inductance, that would be huge, right?
Yeah.
So we ended up designing a board, and we were not really interested in the power supply. We don't need the power supply. We just needed to test our load. So we didn't really want to spend a lot of money on it. And we went to Monolithic Power Systems and asked them if they would help us. And they said, of course. And so we got their latest and greatest modules that they were happy to share with us. And we had ended up building a 2000 amp board using Monolithic Power Systems. And it
I've always
worked.
had very, very good results working with MPS. They are really quite an organization.
They're great, and they come visit me regularly to help me with programming or whatever it is that they need. But then Analog Devices showed up and said, "We got a module too. We think you should build a board with our module," and so we did. Most of the boards are now on their way to APEC, but that's the Analog Devices board, and you can see their
Wow.
module. Um, One of the things that it highlighted was that, there's still a disconnect between power electronics and power integrity. So we have a 2000 amp board, but when we did the step load on this Analog Devices board, the step is about a 300 to 400 millivolt excursion. And power integrity says we're allowed to have 50. So how do we do that? There's two ways to do that. One way to do that is increase the bandwidth of the control loop, which isn't so easy to do on a big board like this, and we're already pushing the bandwidth. The second possibility is to add capacitors to, work against the inductance of the VRM. Currently, this board has 100 tandem capacitors, and we told them we could solve their issue with capacitors, but we need to add another 900 tandem capacitors to the board. And that becomes really problematic, right? I mean, where do you put them? Who's going to pay for them? Adds a lot of weight, all those kinds of things. And so next year, we already have people calling us asking if we would do a vertical power delivery board with our loads. Um, yeah, and we're thinking about it. We'd like to do it. We'd like to do the paper. We'd like to do
Yeah.
anything that supports our devices, right? And we'd like to live at the bleeding edge. But I researched this last week at IEEE, and I came up with about 18 articles on vertical power delivery, and they all talk about DC resistance. I haven't found anybody that talks about the inductance getting from one side of the board to the other. But C is equal to L over R squared, and we can't fix that. So how much capacitance do you need to fix that inductance? This big power board has 20 picohenries of inductance, and that took 1,000 it took 100 1,000 microfarad caps, right? 100 millifarads to tame 20 picohenries. How are you going to get from the back side of the board to the top side of the board? Where would the decoupling caps go? And if you look at the physical size of these modules, and these are pretty small modules for what they're doing, how would you fit 10 of those under the socket?
Right.
Um, so I don't quite understand what they're thinking, but I've yet to see any EM simulations that would show power getting from the back side of the board to the top side of the board. And we'll support them. We've had lots of customers that visit us at the supercomputer conference and also at DesignCon to look at this load. And the reaction was really interesting. We got a much bigger response than we expected. We also had customers that really thought that this wasn't quite enough. We had a customer who's got 2,000 amps, 1,600 watts, but it's a 25 millimeter by 25 millimeter device. We had another customer who came, they got a 115 millimeter socket. Could we put 6,000 amps in their socket? And part of the reason we did all this development is so we would know the answer. We do. We know the answer is L over R. So yes, I can get that to 6,000 amps, and it's going to be slower. I can even tell you how much slower. So people are pushing that boundary. The bigger question for me is, what are they doing with it? I mean, we understood that loads interact with power supplies, and to avoid that interaction, we need to have a higher bandwidth in the load than we do in the power supply. We'd like the impedance of the load, the capacitive, electronic capacitive impedance of the load not to interact with the VRM. Again, it was perfect for that, absolutely perfect for that. And so, pulling that off was really not that much of a problem, but where do you go from here? And how do we scale that to the level they want to scale it at? And why are they actually doing it? So that was the last question that I found the most interesting because everybody visited us, Amazon and Microsoft and every one of these companies visit us. And we asked them why they needed the speed. And they said they want to try to approach the die speed because they're trying to do crosstalk evaluations. What they're worried about is as they shrink the die, all these signals are getting close together. And, we're worried about getting 2,000 amps through the chip. They're worried about getting 1,000 SI lines in and out of that chip without degrading them. And so what they're trying to do is to get a look at how these high speed, very high currents get into their signal lines years before they have the chip. They won't have a chip for a year or two. And yet here they are designing the board, and they'd really like to understand crosstalk. They'd like to understand EMI. They'd like to understand the board design. And to do that, they need the load to approach the speed of the device. And for most devices, that's in the 300 to 500 megahertz range at the package level. There are devices much faster than that, but not in these big packages. And so that's the goal: make this thing as fast as we can make it in a package that uses their cooling systems. They can validate TDP and allows them to look at things like crosstalk.
It's interesting that they're looking at step loads that are basically the complete on and off of their GPUs. I mean, that's
Not always.
quite a requirement.
Yeah, so it is a big requirement. There are supercomputers that do that. I don't know how much of it is public, but there are computers that actually go from almost zero load to full load constantly. Those are the only two modes they have. There are other ones that have different patterns. So, for our 2,000 amp load, it's an 11-bit digital control. So we can go in 1 amp steps from 0 to 2,000 amps. And for me, the coolest thing to see was we were running pseudo random bit streams at 66 megasamples per second. Um, and that's pretty interesting to see. When you measure it on the board, the current really looks like perfect white noise, but 2,000 amps. And so
Wow.
we can see spectral content really nice. If you're doing things like EMI, it's really nice because you're just injecting this very low, large noise signal, and you just measure what comes out. You want to measure large signal impedance? Yeah, we can do pretty clean sine waves at 2,000 amps peak to peak because it's an 11-bit control at 66 megasamples. So, in our demo that we run at the shows, we have linear rise and fall, we have instantaneous rise and fall, we have exponential rise and fall. We have burst modes, we have pseudo-random patterns. It's really just kind of to flex our muscles, but you can do anything you want with those 11 bits. And that gets to one of the other challenges we had is we have 11 bits, but we want them all to be simultaneous. So that means that we have a GaN cell in our load pattern that only has 1 amp. And then we have one GaN load cell that has 2 amps. All of the other ones have 4 amps, total of 513 load cells. If you get to the highest current, the last one is 1,024 amps on a single bit at 4 amps per cell. That's 256 gallium nitride devices connected to that bit. And that's the reason we have almost 2,000 drivers. We have to do fan out control. We have to do propagation delay management. In fact, there are meander lines in the board. We try to time match all of the signals from the bits to the devices so that all of the devices can switch as close to simultaneously as possible. That was a huge challenge because of the density of the board. You know, you can see in here, there's not really any dead space between those load cells. And so
Right.
creating meander lines. And then there was another question, we haven't quite answered it yet. How do you measure the 2000 amp current? And currently we can't. We can measure the current we told it to do. We could try to validate that from average power measurements. Um, there are actually antennas we built into the board. And so every one of these load cell has ground vias and power vias that goes from the top side to the bottom side to connect to the decoupling capacitors. So next to those ground vias, we put a via right next to it. And it just comes out to two pads. And we can very easily see the DIDT in the ground via from the load cell, and then we know how fast the load cell was. We can't measure DC, and customers are saying, can I see the 2000 amp signal? And the answer is you can't because it doesn't exist in any one place. You would have to measure the current in every cell. So if you want to actually measure that dynamic current, I don't know how it would be possible to do it. But we can look at individuals from the new fields.
Have you considered doing like immersive liquid cooling instead of the heatsink liquid cooling?
Yeah, we did, and we are talking to some companies about it. We can certainly do it. Um, it's not nearly as effective as the refrigeration cooling. So when we were at the supercomputer conference, we were looking at how many cooling companies that were there. It was huge. I mean, it was there were a lot of people that were just doing cooling, but there weren't many of them doing immersion cooling. Most of them were doing refrigeration cooling, and the reason is it's just so much more efficient. So if you wanted to immersion cool this, we would probably still bring it out to a manifold, and the manifold would look, just like this. Inside this channel, it's a relatively thick channel. We have the fins that the water runs through. And so what we would probably do is just use the bottom half of this manifold, and you just see the fins thicken up, and then you could immerse this. It would work fine.
How about phase change materials? Did you look at any of those?
We did. I mean, we're looking at everything that's available. We talked to Maxwell Labs, they're using focused light to remove heat and haven't decided quite how effective that is yet, but it's kind of bleeding edge, and they're saying that it might be really good for our tiny little probes to use light to get the heat out of it. And I don't know exactly how that works, but they create these focal lenses that improves the radiation cooling of the device, and then they bring it out through a little aperture, and we are evaluating that. We have almost every company working on improved materials, both like gap pads, thermal pads. We actually have some that are custom made for us, and also the thermal compounds. The problem with the phase change material is that it's really hard for us to manage that dimension between the gallium nitride, the resistors, and the cooling, especially when you talk about the fact that we have 513 resistors and 513 gallium nitride elements in that single array. And we need to try to manage that distance between every one of those devices in the cooling system. So in a phase change material, which is really thin, it becomes difficult for us to manage that, but certainly we're looking at it. In this device, our line injector, I mentioned that this is the highest thermal density we have, about 140 watts in a 12 square millimeter device. That one's really difficult. We can actually watch how to adjust the cooling system by looking at the voltage across the drain source of the GAN FET. It's a self-biased device. And we can see as we torque the screws, the voltage goes up and down, and we know have that uh, when we have the plane exactly straight, because we'll end up with a minima in that voltage drop. Of course, that's kind of an expensive
Interesting.
way to tune the cooling
Yeah.
system, but we use that to figure out where it is that we're at. And of course, the more pressure we can exert on the gallium nitride and the resistor, the better the cooling is. What we don't know really is how much pressure we can exhibit on either one of those before they crack.
Well, we have that data, by the way, on our website in the reliability reports.
Okay,
So
yeah, that
yeah,
would be really
so we've
helpful.
actually done it on exactly your device, I believe, as well.
Oh, cool. Yeah, I'll take a look at that. But rent again, we have this array that's got 513 devices in it, and they're not all going to be the same. We have tolerances in height. We have
Yeah, that
tolerances.
That could be
thicknesses.
the problem is one heat sink on 513 devices. You could have, pressure points.
Yeah. So, but most of the companies, most of the big thermal companies have lent us beta materials that they have to evaluate where they have much higher thermal conductivities. We have some pastes here that are in the 50 watt per meter K range. We have one that's at 80 watts per meter K. And then the question really becomes, what's the best way to manage the thickness of that layer so that it's uniform and across the
And does
500?
does it maintain that during many cycles? We've seen some that degrade.
I'm sure they do, and we haven't done any real cycling tests yet. We're hoping to build more of these boards. They're obviously expensive boards, and so what we're waiting for is for customers to buy some of these, and customers are buying some of these as demo boards just because they're not at 2,000 amps yet, but they're trying to learn how to make these measurements, and this is a really good opportunity for them to do that. And so once we have more boards, we'll start to accumulate more data and we'll learn from customers what it is that they want to do. But for us, the difficulty really was in the development of a single load cell, which is it's minuscule. It's about the size of a 1206 resistor. And
Wow.
that's what we're working on is optimizing that. And sometimes we're using that in a linear region, and sometimes we're using it in a switched region. And obviously those are two different things. Um, but when you look at across the array of devices that we make, it all comes down to we need really fast devices, and we need them to be really small, and we need them to have really low resistance. And it would be really beneficial if they're inexpensive. And all of those lead you to GaN. And so if you tried to do this with silicon, you just wouldn't be able to get there. And so that's what we're exploiting. We're exploiting that.
Yeah, you mentioned about some of our older devices are the ones that you like a lot. That may very well be because they're rather large for the amount of current they handle. And as we go
Correct.
to newer generations, the current density goes up, which may not play to your advantage. But we have no intention of discontinuing those parts that you're talking about.
Yeah, that's really good to know. And I mean, we could talk about that one of these days offline. It just looks like the replacement devices are higher current devices, but they also have higher CGD. And the devices that we're using, we
The figure of
selected for
merit,
those. Yeah,
the R-on CGD is still lower. It's
yeah.
about generation to generation runs about 25 to 30% lower per generation.
Based on your RG, but when you add our driver, then we just become really sensitive to CGD, and we can't really get our driver resistance down. Right now, we're using almost 1,200 drivers,
Hmm,
and um,
got it.
eventually, maybe we'll be able to get better drivers, but not right now.
I understand. It's driver limited then.
Yeah.
Yeah.
But I mean, Picotest is a company that responds to customer demand. We build crazy things because customers need us to build crazy things. And so if it's something that you could buy off the shelf, we would always tell our customers, just go buy it. We'll even help you integrate it. But if you need something crazy, we'll do it. And so I think what we have now is something that proves that we have the ability. Now what we're hearing from customers is what they want us to do with that. Um, and that's where it starts to get interesting. We got a customer who wants 6,000 amps. We've got a customer who wants, 5 times the density we're at right now. Van Dannen at Northrop, he purchased one of our first loads and he wanted to do 7 domains simultaneously. And that was interesting because we discussed that with him too. What's the purpose of that? And the purpose was measuring crosstalk of the 7 power domains. There are actually 23 power domains in their chip. There are 7 critical ones, and that's what they wanted to use our device for, is to look at the crosstalk between devices. For us, it's just load cells. We can fit so many load cells in the package, and that'll define how many bits you can get and how much current you can get, what speed you can get. And so we just arrange them in a way that power those 7 domains. And if we wanted higher power density, we can achieve it. Your devices can do a lot more current than we're running them at. And the resistors can do a lot more power than we're running them at too. We just have to trade off speed. And so pick one. You get to balance those two. And however you want to balance those will help you do it. But that's the trade-off.
Well, I mean, I am always every time I talk to you, I'm just amazed the limits that you push things to, which are well beyond anybody else I know of. And maybe
Thanks.
it's why you take on crazy things. I don't know.
Yeah, it's probably one of those things that drives me is the challenge. I love the challenge. That's funny because I was trying to slow down. My wife says you need to slow down, and Analog Devices called. They said, we've got these old preamplifiers that Jim Williams made for us, and the old ones that were in the cookie tins, and they're down to one, but they really need a higher gain, lower noise device. Could I make one for them? And I thought about it. I said, I'm really busy right now. I don't think so. And they said, so you're willing to concede that you can't build a preamplifier that's better than the one that Jim Williams built? And I hated them for that because I went right to the lab. It was like, of course I can. Um, and sure
You're
enough, I was
too
driven.
easy, Steve. You're too
Yeah, I
easy.
was. I was driven. I was driven to do it, and I delivered it. They were happy, and I said, "Don't pull that one again." I'll let you off this time, but not again. But I think that's what I live for. It's the challenge, and I think that everybody in this business is here because we love it. You wouldn't stay here if you didn't love it, because it's so much work, right? And I think that everybody plays their role. We couldn't do this without you, right? And I know you going back, from the IRF 100 samples I get back in 1979, I think it was, and you've always made these great.
78. Yeah.
Yeah, yeah, I know it was around that. I was working on the space shuttle back in those days, and I remember getting my samples. So, the devices keep getting better, and that means the demand keeps getting bigger. And everybody's doing these crazy things. I'm just one piece in that puzzle, enabling somebody to move something out of the way. When people ask me, how do you do these crazy things? I say, it's actually quite simple. You figure out what's in the way and you remove it. And after you do that, you're going to get better performance, but something else is going to be in the way. And you figure out what that is, and then
Yeah.
you move it. And that's what we do. We do that year after year, figuring out what's in the way and moving it.
Yeah. My philosophy is until you can prove it can't be done, it can be done.
That's a good philosophy. In fact, I remember back in the 1990s, we got a spec from Hughes for DirecTV. They wanted us to build a power supply that was 1 volt output and 90% efficiency, and we laughed. And we said, obviously, these guys don't know much about power supplies, right? I mean, we were using synchronous rectifiers even back in those days. And they invited me to El Segundo, and I went. And it was power supply on the bench. They said, you can measure it yourself. It's more than 90%. And I said, so if you already have that power supply, why do you want us? And they said, for us, it costs $1 million to do that. We don't want to pay $1 million for it. We want you to do it cheaper. But I learned, early in my career when I still had this big chip on my shoulder, thinking I was God's gift to the universe, that there were other people on this planet that were really smart too. And I learned that, you don't doubt it until you've seen it. Same thing, we were working on ground-based radar and we were building high-density power supplies. They wanted a 8 volt, 400-watt brick to replace the Vicor bricks, but they needed to be really low inductance because they were doing these phased array switching, and so they had an excursion at 2 nanoseconds. And we laughed again and said, "There's no way you'd be able to switch that much current in 2 nanoseconds, and we might be able to meet it on one side of the output pin, but not the other." And they invited us to Maryland, I think it was, to see their system, and they had probes, near field probes, to show us how fast it was. And what they were switching was these RF things. They were turning these RF things on and off. And sure enough, it went from 0 to up in 2 nanoseconds. And they said, "See." And so I learned there's a lot of smart people in this world, and we
Yeah.
each do our thing. And if we do it right, then all of those things blend together and we all accomplish what we want. So there's this great synergy when we get to work with this group of really smart people that do these things, which, I don't know how many people can claim to have developed both the MOSFET and gallium nitride FET. I think you're probably the only one. So it's got to feel pretty good knowing that, for 50 years, you've driven technology, and a lot of what we do is because of people like you.
Well, thank you very much. I stand on the shoulders of giants and I rub elbows with giants like you. So it's
Right.
really all a big effort of a lot of people in this industry. And it's one of the reasons, I've stayed in this industry is because there is an incredibly inspiring group of people here. It's not
Oh, yeah,
something that many people, know about. You can't go to a cocktail party and talk about, power electronics. But it really has attracted a phenomenal group.
yeah,
And just over so many years, I met the smartest people that do the most incredibly difficult things. And it's just fun. If it weren't
yeah.
fun, I would have stopped, you would have stopped, but it stays fun.
Yeah, that's what I said. We got to be getting something out of it. Otherwise, we wouldn't be doing it anymore. We do this because we love doing this. Um, I told my wife, I don't know how to stop. This is,
Yeah.
it's just there. It's there and it's always on. And yeah, it's crazy to do the things that we do, but somebody actually designed that chip that's consuming the 2000 amps, right?
Yeah.
And so you got to remember that. I tell people that when they tell me that they want to do AM simulation, but it's too hard, blah, blah, blah. I tried it. It's very complicated. I said, I'm only asking you to use it. Somebody else got asked to write it. Uh, and so, you gotta try to remember that. And so I think as I get older, I get more humble and I realize that there are really very smart people doing really crazy things. I'm just helping them move stuff out of the way. That's all.
Me too. Let's keep doing it for a while, huh?
Oh, I think so. I think so. And I hope to see you again soon. Uh,
Yeah, I'm sorry I'm gonna miss you at APEC. But hopefully we can get together between that and PCIM. It's
yeah,
always my
absolutely.
challenge.
Yeah,
All
and when we
righty.
get yeah after we get from APEC, we're gonna have some of these 256 amp high speed board demos. And if you want, I'll send you one. It just has a little demo board. You plug it in and it'll go and it'll run the pseudo random patterns and all that stuff,
Oh,
just to give me a
wow.
feel. And you can actually watch one. So if you want to see one of these things play, let me know. We'll send you one.
I definitely want to see it play and stand back with safety glasses while I do.
And wear your brown pants.
Yeah, right.
So anyway, it's been fun. It's
Yeah,
great to see you.
always
And
fun, Steve. Keep it up and I'll see you soon. Thank you.
and thanks for your great devices.
And thanks for your work too, making the state of the art go forward. That's what we
Yeah,
need.
that's what we do.
All righty.
Have a good one.
Bye-bye.